Turbochargers work incredibly hard. They are forced induction devices. They use exhaust gases to spin a turbine. This turbine then drives a compressor. The compressor forces more air into the engine cylinders. This means more power. The turbine wheel can spin at speeds exceeding 200,000 revolutions per minute. The exhaust gases passing through the turbine housing are extremely hot. Temperatures can easily reach several hundred degrees Celsius. This intense heat is transferred directly to the turbocharger components, especially the center housing. If a turbocharger gets too hot, serious problems will occur. The extreme temperatures can cause the metal components to distort or even melt in severe cases. More commonly, the bearings supporting the rapidly spinning shaft will fail. Engine oil, which lubricates these bearings, can also suffer. High temperatures cause the oil to break down and degrade much faster. This process is known as oil coking. Burnt oil leaves behind hard carbon deposits. These deposits can block vital oil passages, leading to oil starvation and catastrophic turbo failure. Efficiency also drops significantly with excessive heat. Cooling systems are therefore absolutely essential for turbocharger survival and performance. They are not an afterthought in design, they are a critical element. The primary purpose of any turbo cooling system is to manage and dissipate the immense heat generated during operation. By keeping the turbocharger's core components, particularly the center housing rotating assembly, CHRA, within their design temperature limits, the system ensures longevity. This also allows the turbo to consistently deliver the expected boost pressure and maintain engine performance levels. There are primarily two methods employed to cool turbochargers effectively. The first and most traditional method relies on engine oil. The second method utilizes the engine's coolant, which is predominantly water mixed with antifreeze. Many older or less demanding applications might use oil cooling exclusively. However, modern vehicles, especially those with high-performance engines, frequently employ a combination of both oil and water cooling. Each system has its own distinct advantages and inherent limitations. We will delve into these aspects in the following sections. Oil cooling is a fundamental aspect of turbocharger design. It is often the first line of defense against heat. In an oil-cooled turbocharger, engine oil is supplied under pressure. This oil comes directly from the engine's main lubrication system. It is routed through an inlet port into the turbo's center housing. This is where the shaft, turbine wheel, and compressor wheel are all supported by bearings. The oil flows over and around these bearings. This action serves two vital functions simultaneously. It lubricates the bearings, reducing friction. It also absorbs heat from the bearings and shaft. The main advantage of oil cooling lies in its inherent simplicity and dual functionality. The engine already possesses a sophisticated oil circulation system. Tapping into this system to supply the turbocharger is a relatively straightforward engineering solution. The very same fluid that provides the critical lubrication film for the high-speed bearings also acts as a coolant. It carries away a significant amount of heat. This heat is then transferred back to the engine's oil sump. From there, it can be dissipated via the oil pan or an oil cooler. For many standard applications, this is sufficient. However, oil cooling on its own does have notable limitations. Oil has a lower specific heat capacity compared to water. This means it is less efficient at absorbing large amounts of heat. Under extreme operating conditions, such as prolonged high-boost driving, the oil temperature can rise excessively. A more significant issue is heat soak. This occurs when the engine is switched off after a hard run. The turbo is still incredibly hot, but the oil circulation stops. The stationary oil within the hot center housing can then overheat and degrade. This overheating of static oil leads to oil coking. The oil essentially burns, leaving behind hard carbon deposits. These deposits are highly detrimental. They can clog the narrow oil passages within the turbocharger. They can also act as an abrasive, accelerating wear on the bearings and shaft. Over time, this can lead to restricted oil flow, oil starvation, and ultimately premature turbocharger failure. Therefore, while oil cooling is essential for lubrication and provides some cooling, it often needs assistance in more demanding scenarios to prevent these issues. Water cooling provides an additional and often more potent method for managing turbocharger temperatures. In a water-cooled turbocharger, dedicated passages are incorporated into the design of the center housing. These passages allow engine coolant to circulate around the hottest parts of the turbo. This is typically in close proximity to the bearings and the turbine side seal. The coolant is supplied from the engine's main cooling system. It flows through the turbo and then returns to the engine's cooling circuit to dissipate the absorbed heat via the radiator. The primary benefit of water cooling is water's superior heat absorption capability. Water has a significantly higher specific heat capacity than oil. This means it can absorb and carry away much more thermal energy. This is particularly effective in reducing the soakback of heat from the extremely hot turbine housing into the CHRA. A crucial advantage of water cooling is its ability to continue functioning even after the engine has been switched off. This is due to a phenomenon called the thermosiphon effect, which is incredibly useful. The thermosiphon effect works because hot water is less dense than cold water. When the engine stops, the coolant within the turbo's water jacket is very hot. This hot, less dense coolant naturally rises. Cooler, denser coolant from the engine block or radiator hoses is then drawn into the turbocharger to replace it. This creates a slow, passive circulation of coolant. This circulation continues to draw heat away from the turbo's critical components for some time after engine shutdown. It significantly mitigates the risk of oil coking. Despite these considerable advantages, water cooling also has points to consider. It inherently adds complexity to the turbocharger system. It requires additional plumbing, including hoses and connections for the coolant. Each of these connections represents a potential point for leaks to occur over time. Furthermore, water itself provides no lubrication whatsoever to the turbocharger's moving parts. The crucial task of lubricating the bearings still falls entirely upon the engine oil. Therefore, water cooling is a dedicated thermal management system, complementing the oil's role. The combination of both oil and water cooling systems represents the most robust solution for turbocharger thermal management. This dual approach is now commonplace in most modern turbocharged petrol engines. It is virtually standard in high-performance and heavy-duty diesel applications. The oil system continues to perform its indispensable role. It provides the vital lubrication for the high-speed shaft and bearings. It also offers a continuous primary cooling effect during all phases of engine operation, effectively removing a base load of heat. The water cooling system then acts as a powerful ally. It significantly boosts the overall heat dissipation capacity of the turbocharger unit. By circulating coolant through the center housing, it helps to keep the bulk temperature of the CHRA lower and more stable. This in turn helps to keep the engine oil in contact with the bearings at a more optimal temperature. This slows down oil degradation and extends its effective life. Critically, the water cooling system provides superior protection against the damaging effects of heat soak after the engine is shut down. When a hot engine is turned off, the oil flow to the turbocharger stops instantly. However, the immense residual heat stored in the turbine housing continues to radiate into the center section. Without water cooling, the stationary oil in the bearing housing would quickly overheat, leading to coking. With a water-cooled system, the thermosiphon effect takes over. Coolant continues to circulate passively, drawing this dangerous residual heat away. This prevents the oil from burning and protects the bearings from excessive temperatures during this vulnerable period. In summary, employing both oil and water cooling provides a synergistic advantage. The oil ensures continuous lubrication and provides a fundamental level of cooling. The water system adds a much greater capacity for heat removal, particularly under high load conditions. It also offers crucial protection against heat soak after engine shutdown. This comprehensive approach ensures the turbocharger operates with greater reliability and durability. It allows for sustained high performance and significantly extends the service life of this critical engine component, making it the preferred method for demanding applications.